Good afternoon, everyone. Welcome to session 2. Welcome back if you're at session 1 this morning. If not, welcome to session 2 if you're new. I'll just wait for a few other delegates to join, and then we'll make a start in probably about a minute's time. Okay, let's make a start. So, good afternoon, everyone. Welcome to session 2 of this Cornwall Flow Accelerator project, floating offshore wind webinar, looking at materials and manufacturability. I'm Simon Cheeseman from the Offshore Renewable Energy Catapult. So just a bit of normal housekeeping. The sessions are now being recorded. We will make the slides available after the event. They'll be posted onto the Celtic Sea Cluster website. That website address is in the chat already, along with my email address and Julie Taylor, who's our innovation manager in the Southwest, her email address. Please look at the cluster website. Please think about joining the cluster as well. It's the thing that's helping to set the scene for the Celtic Sea floating offshore wind deployment in terms of looking at market readiness, looking at grid, looking at port infrastructure, looking at supply chain capability, and working with the Celtic Sea Developers Alliance, BAYS, and the Crown Estate, but more of that to come. There'll be a short questions and answers session after each agenda item, if we've got time. But otherwise, at the end of the session, there's an overall questions and answer session. In this morning's run through, we managed to get through questions after each presentation, which was good. There is a polling feature in Zoom, and we'll be using that after each of the first 2 presentations to ask some questions and really look to see from a delegate's perspective how much interest there is in follow-on deep dives to some of the project topics that we'll be covering. Behind the scenes, we've got Vicky Sharp from the Offshore Renewable Energy Catapult, and Vicky's managing Zoom, making sure that behaves properly. And as I mentioned, Julie Taylor is also working behind the scenes, just keeping an eye on delegate questions to make sure that we address all of those. So this session and this webinar is a game of 2 halves. We've had the first half this morning. We're now about to talk about foundations, anchoring and mooring. We'll run till 4 o'clock. And the idea of this webinar is really the first in a series of industry engagements that Cornwall Flow Accelerator is running. And these are designed to really sort of scope out the opportunities for floating offshore wind in the Celtic Sea. We're using what we term a sort of blade to anchors approach to look at the various innovation challenges. It's about trying to bring industry up to speed in looking at what the current state of the art is in terms of materials manufacturability, and thinking about how can we drive out sort of carbon content and look at sustainability in our manufacturing processes in the future. We're very keen to help the supply chain be part of floating offshore wind, and also try to help developers achieve sort of targets for local content that's being driven by the offshore wind sector deal. So as I say, this is about trying to tell you, where we've got to so far in looking at component technology, and where we think the state of the art will go in the future, and where there are opportunities for innovation challenges and supply chain involvement in the future. So just to put things in perspective, what is Cornwall Flow Accelerator? It's an ERDF funded project underway now and running out till June 23. It's about trying to do the groundwork for floating offshore wind in the Celtic Sea, trying to understand what that pipeline will look like, trying to understand what the technology challenges are, where the logistics pinch points might be, and helping to supply, the sort of regional supply chain to get ready for this, and support work with project developers going forward. So the Cornwall Flow Accelerator projects led by Celtic Sea Power. They were formerly known as Wave Hub Development Services, and they're supported by the universities of Exeter and Plymouth, and ourselves, the Offshore Renewable Energy Catapult. So we're all working in collaboration, and what we're doing, four main things. One is deploying a floating LiDAR, two floating LiDAR into the Celtic Sea to collect wind resource data. They will be deployed, I'm going to say April or May, and some of that data will be made publicly available. So if that's something you're interested in, you need to contact us at Cornwall Flow Accelerator. Importantly, we've built, and Exeter University are leading, a numerical simulator model that enables us to model 500 megawatt plus arrays and start to look at some of the engineering issues around port requirements, vessel requirements, different technologies. And as that numerical simulator model matures, added to that will be a DP vessel simulator, as well as a bridge simulator. And the idea is to start to link it to some other university test facilities as well, so that we can do some real in-depth analysis and what-if analysis, looking at the impact of different types of technology innovation. There's a lot of research that's being conducted. You're seeing for the first time the outputs of some of that research today. And there's a general call to arms to encourage you delegates to get involved in the next phases. And we need feedback from you to tell us what you're interested in and what you think you'd like to explore further on down the line. So where does the CFA Cornwall Flow Accelerator fit into the wider scheme of things? We've established something called the Celtic Sea Cluster. The cluster is there to do three jobs. One is to help establish the market, working with the Crown Estates to understand the leasing round, working with the government to understand the contracts for difference timings, also looking at funding for ports investment, and also linking with something called the Celtic Sea Developers Alliance, which is an alliance of all those developers who've got an interest in the Celtic Sea. So the Celtic Sea Cluster formed last year in late September. The website details are in the chat. Exists as an entity with a board. The board's made up of Welsh Government, Cornwall Local Enterprise Partnership, Marine Energy Wales, which is the trade body in Wales, Celtic Sea Power, which was Wave Hub Development Services, and ourselves, the Catapult. And we were really there as an interim board to help develop the cluster and stand it up and look at these market issues. And then we're there also to act as a voice for the supply chain to help accelerate that supply chain, get it ready for procurement calls that are going to come down the line. And at the end of the day, we're there to help create sustainable regional jobs. In terms of floating offshore wind, then this slide just sort of puts it in context from a UK and a sort of rest of the world position. I think these are fairly pessimistic numbers. I think it could be a lot bigger than this. We know in the Celtic Sea there's around 150 gigawatts of resource potential. It's a question of how much of that do we think we can extract, and really what is the vision for floating offshore wind in the Celtic Sea up to 2050. The Crown Estates have set the vision for 4 gigawatts by 2030. We need to understand that's great, and that provides some challenges in its own right. But obviously we want to know and work out what is that vision beyond that, And that's some of the work that the cluster's doing at the moment, where we're developing a regional strategy for Wales and the Southwest. From that will flow regional plans. And from that will flow the ambition for the amount of floating offshore wind that we think we can harness in the Celtic Sea. Just a quick, this is additional slides that weren't available this morning, so you get a bit more for your money if you stayed on. This is the governance model for the cluster. At the moment, there's just that monthly executive committee that sits in the middle, and a number of working groups that are working on key aspects of sort of market creation and supply chain opportunity. We're fed in by, we've got feed in from various regulators, but the view is that we want to make the cluster, make it more representative of the regions that are around that are interested in the Celtic Sea. So we're thinking of moving to a two sort of board model, one with a quarterly strategic board that would have the various regions represented, along with Bays and the Crown Estates, and then a monthly executive board that is actually doing the sort of more tactical work to keep things moving along. I will point out that Bays are already an observer on our existing executive committee. The Crown Estates are also an associate member, and we've got a formal link into the Celtic Sea Developers Alliance. Excuse me. Just a bit of a timeline for the Celtic Sea. And again, this is a slide I didn't show this morning, just a bit of extra value for money for staying on or joining in the afternoon. This starts to show the rollout of and potential first generation of the test and demonstration projects, followed by the early commercial arrays, showing that we can get to the government's target of 1 gigawatt by 2030. But we will start to see some pinch points around ports availability. And then below the line there, you can see the activity that the Crown Estate need to go through that they've already announced will be happening in terms of defining through spatial planning what the actual key areas will be, and also looking at how those leasing rounds are going to be conducted. As we move on from 2030, then we move into large-scale deployment, volume manufacture, and a growing operations and maintenance requirement. And so by around sort of 2036 at 4 gigawatts, we've got 200, at least around 268 50 megawatt turbines. A lot of turbines, a lot of blades, a lot of platforms, a lot of moorings and anchoring. And then from a ScotWind perspective, this is just our own internal analysis of where we think certainly the first stage developers will be switching on around a similar sort of time. So, bit of competition for port space, bit of competition in the supply chain. Bearing in mind there are markets elsewhere as well. France is starting to develop now. Southern Ireland not far behind, and obviously markets in the US and Asia are coming along. So it's going to be a very, very busy time. But the focus here is all about regional content and trying to make sure we get it right in the Celtic Sea, that we have a decent blueprint and strategic approach for the Celtic Sea, that we collectively work together to make the most of this as we can. So here's the afternoon's agenda. Our first presenter will be our own Dylan Duncan. He'll be talking about foundations, different manufacturing types, different sizes, and looking at some of the low carbon manufacturability opportunities there. We'll then have a polling question on that to gauge your interest, and then follow up with questions and answers. Following Dylan is Ellen Jump, one of our project engineers. Ellen will be talking about anchoring and mooring. Similar sort of issues, what's the state of the art at the moment? What's likely to happen in the future? How do we reduce costs? What sort of alternative materials could we be using? And again, then there'll be a polling question to get a first cut of your interest in that particular topic. And and while we're asking those questions, if there's something you're particularly interested in, do raise a question in the questions and answers. Do send us your details and contact details if you want to be involved in the follow-up deep dive sessions. After Ellen, we're really pleased to have Ollie Stubb from BW Ideal join us. Ollie's the Business Development Manager, Northern Europe, and he'll be talking about their aspirations for concrete hull fabrication. If you were in the presentation this morning, you would have heard Guy Raymond from RWE talking. There's a couple of points in there that Ollie wants to pick up and correct in terms of size of platforms. So it's great that he's available. And then finally, a questions and answer session, just looking back over not only this afternoon, but the whole day, if you were involved in this morning's session, and a chance for final sort of questions and answers. So I'm just going to check to see, I can't see anything in the chat or in the Q&A. So I'm going to ask Dylan to step forward and load up your slides, Dylan. And the floor is yours.
Perfect. Thank you, Simon. Just 2 seconds.
There
we are. And you should be seeing the full screen there now.
Yep, see the full screen, hear you perfectly. So thanks very much indeed.
Perfect. So hi, everyone. Hi again, everyone, should I see, if you weren't sick of the sight of me this morning. And for all of you who weren't in the morning session, welcome. So my name is Dylan Duncan. I'm a research engineer here at ORE Catapult. I've been participating on this project for looking at potentially reducing emissions from wind turbine towers and floating foundations. And that's the basic stuff from that work is what I'm going to be discussing about this afternoon. So just as an agenda, we'll be looking at the kind of current state of the art for offshore floating foundations. So for those of you that watched my tower presentation this morning, I kind of went over what the baseline design was, and I looked at what else was in the industry. With the floating sector, there isn't that baseline. So I'll be going over each of the kind of core structures, their pros and cons over each other, just as a general overview, and then we'll look at some opportunities that can be had there. I'll compare the 2 core materials that are used in offshore floaters, and I'll also discuss what I think I'll be using as a kind of reference floater for the rest of the project as well. So I basically had this exact same slide on in this morning's presentation. So this project or this work package as part of the Cornwall Flow Accelerator is effectively looking at the opportunities for reducing the carbon footprint for floating wind turbine foundations. And we're doing this via 2 kind of steps. First step is to carry out a literature review, which will help highlight the trends and interests in industry and academia. And that will help us gauge where the kind of opportunities lie, where the interest lies within the industry. And then afterwards, I'll define a reference structure with a view of using that structure to engage with kind of local supply chains and industry partners to discuss about how we can best assess the carbon emissions from that. And we'll do all that by defining kind of a chosen site conditions, establishing a reference structure, defining our life cycle definition, and carrying out our LCA, like a detailed LCA analysis. So just as a problem statement, so floating wind's a relatively new technology, at least with regards to kind of mainstream knowledge. But it's really kind of shooting up over the years, and Simon showed his chart in his earlier presentation this morning. He also mentioned Scotland, and Scotland alone will produce over 14,000 megawatts, and that's just in Scotland alone. So we're going to be seeing a lot more floating wind turbines. But if you look at the graph on the bottom left of the screen there, you can see that in blue, the foundations for a floating turbine take up quite a substantial chunk of your overall emissions. And if we're going to be building all these floating wind turbines, I think it's important to consider where we can best reduce those emissions. So here I'm going to give a very general kind of overview as to the kind of state of the art for each of these structures. I'm going to go over some kind of brief pros and cons for each. This isn't aimed at any particular one design, it's just a very general overview. So if anyone's working on, you know, a super superior semi-sub, feel free to get in touch. But yeah, we'll start off with the semi-sub. I mentioned there's no baseline kind of floating designs. Semi-sub is probably as close as you get to one though. It's the most commonly used, and I've got a chart that will show that later in the presentation. Consists of a series of columns for structural stability and pontoons for actually making it float. It's generally got poorer stability than other foundations, but it's flexible in terms of its depth range. And I've seen some designs as well that allow it to be installed, like you can effectively assemble the turbine dockside and then tow it to site. So there's some interesting advantages there. It's from a kind of marketing point of view, it's global market's a bit higher. The technology readiness level, the TRL, is also a bit higher. And there's kind of, generally speaking in the industry, there's more sort of reference material there as well that I can look at as well. Another kind of more common one is the spar. So that consists of one single vertical buoyant cylinder, and that's kept afloat through kind of a ballasted draft underneath. I've seen some interesting kind of conceptual designs for spars where they'll have like moon pools and things built in, which helps give it quite high stability. But depending on the structure you're looking at, some might have lower stability or higher stability. It's a simpler concept in terms of manufacturing. As you can see, like because of the way, like the shape of it, you can use similar kind of fabrication or manufacturing processes that you would get for your tower. So there's a bit of synergy there, which can simplify things. But because spars are long structures, they're generally only better used in deeper water. And it also brings extra challenges to transportation and installation as well. Barge, we've got our guest speaker from Ideal, so I'll keep the barge speak to a minimum for him. But big advantage with barges is that you can install them at ports and you can effectively sail them into deeper water without taking up too much space. They're heavier structures, but that makes them lend themselves quite well to larger wind turbines as well. DLPs, it's another it's a lower TRL design of TLP, but it's one that's becoming slightly more popular, I think. It's got a similar core structure like that of the semi-sub, but it's made more unique due to the kind of tension mooring system. And Ellen will be speaking more about anchoring and moorings later as well. But that mooring system makes it one of the more stable structures. And because of how much work that system puts in place, you can make the actual core foundations lighter as well. So in terms of just the floating foundation side of things, it's probably one of the more environmentally friendly ones, just for the fact you're using less materials. Good for higher depths, but generally not useful in shallower water where you're going to get more fluctuations in terms of like your water depths. And they're also a bit more susceptible to higher dynamic frequency loads as well. Just some other very high concept designs as well. So the model on the left is made by a company called Offshore Kinematics, and this is their kind of wind turbine support structure. It's very similar to what a typical monopile design would be. I believe it's kind of floated like the actual system. I've not seen it in action yet, but the idea is that it's effectively a monopile that kind of free floats. So it's quite an interesting, quirky design that kind of draws the line between fixed and floating as well. You've also got the tri-vane concept, which I guess in some senses is similar to that of like a barge design, where it's effectively on a ship, is effectively what you're building your wind turbine on. And that makes it well suited to steering and aspects like that as well. So just as a kind of general, what's going on in the industry. So these numbers are rough. They're not, I've not really proofread them, but I hope they give a good idea of what's going on out there. So out of kind of a project, like I looked up how many projects are outgoing in the industry or are currently active, and it totaled up to about 57 in terms of like what floaters are out there or what floating flotation projects are currently active. And out of those 57 projects, I noted that 30 were semi-subs, 9 were spars, and then afterwards it kind of decreased at that point. So you're looking at over half of all floating foundations are semi-subs. These numbers might not be entirely accurate, but I think they provide a good breakdown as to the kind of state of the current industry right now. The big table on the right is just a kind of smattering of projects that I picked for specific structures, spars, barges, semi-subs, and TLPs, just to give an idea of dimensions and masses. So generally speaking, concrete structures are always going to be a bit heavier. Barges are a bit bigger, but you've also got, say, this EO-Link semi-sub. It's supporting a 15 megawatt turbine. It's massive. So it's to give you an idea of how big these structures are, and potentially there's potential for reducing or improving our kind of emissions output from the materials there. And speaking of materials, apologies for this very texty slide. Generally, in floating foundations, only two materials have really been applied, should I say, in projects to this day. Almost a bit like wind turbine towers in that sense, and that's steel and concrete. So they both have their pros and cons over each other. So with steel, your core advantages are that it's well established in offshore wind energy. We have the know-how, and because of that, we can potentially assemble components faster. It's also a lot lighter than concrete as well. So I touched upon that in the tower presentation this morning, where concrete might perform better from an LCA standpoint, but because you're making the tower heavier, that puts more pressure on making your foundation stronger to support that. And this kind of plays into that, where you need to be quite selective about the whole turbine overall, as opposed to just the floating foundations part of it. But generally speaking, steel can be quite expensive and prices fluctuate a lot. And you also need a lot of kind of specialized equipment. So Guy mentioned this morning that there's a limited amount of cranes to be used and aspects like that, which make the manufacturing set parts more challenging. With regards to concrete, you're a bit more adaptable to local conditions and project requirements. So I touched on the manufacturing processes in the tower presentation this morning. And I feel like from a UK perspective, we're stronger with concrete than we are with steel. We don't really make steel in the UK anymore, unfortunately. It's also a bit cheaper, and your kind of internal storage requirements are less, so you might not need a huge kind of factory just to store components either, or materials. Problem is with concrete is that its usage in the wind industry is less, so there's kind of less scope or less reference material to look into for improving that. It's also a lot heavier, and when it comes to manufacturing, you need to take into account processes such as pre-tensioning. Might also be affected by weather conditions as well. There's a lot of kind of weighing between the two. And with that in mind, we've run an initial LCA. So effectively what we've done for this initial LCA is we set a reference structure for a 15 megawatt semi-sub based on the kind of Voltern US model that's publicly available. This is a very high level LCA. We made a lot of assumptions. So we assumed the project would be lasting for 30 years. We picked a pretty standard CTV O&M strategy, one offshore substation. Cables were set to 66 kilovolts. We had representative UK carbon. So some of the aspects that we had to map in our LCA, we took numbers from, like, say, Dutch companies and so on that we had data from other projects for. And we also discounted transportation as well, which is quite a substantial thing to take into account with regards to floating. But we found that concrete vastly outperformed any of the different types of steel. Probably about 40%, I'd say, of the overall emissions for concrete. I feel like in retrospect, because we made so many assumptions, the actual difference wouldn't be that significant, but I think it's quite telling that concrete outperforms steel by that much. So what about future opportunities? So as I mentioned, we still don't have that baseline structure that we get from the tower. and with good reason. Wind conditions, offshore wind energy is really challenging to build a set foundation for. Different foundations will be best for different sites. Your sedimentation as well, what your seabed is, would impact what your moorings you're using, and those moorings will be better suited to certain types of structures. So there's a whole chain of events there that explain why we've not designed that kind of core base structure. But there's always, I think, interest on our market in looking at new structures or optimizing designs. So these three diagrams here are all from patents of varying ages. So the one on the left kind of uses a paddle design to kind of keep it stable. The one in the middle is actually for a vertical axis turbine. It looks like something that would be potentially lethal if you fell into it. But it's quite an interesting design in terms of it's a freely rotating design. The whole floor can rotate, which I thought was quite funky, frankly. And the design on the right is very similar to a semi-sub design, but with multiple turbines on one structure instead. So that could be quite an efficient way to approach these installation problems. So to continue on with future opportunities, we've got new materials. So right up until this point, we've only used steel and concrete. What about something like composites, for example? So something that's a material that's naturally quite weather resistant, I'd say. It would be very complicated because some of these structures can be very complicated and composites are very hard to manufacture, but there could be a market out there for looking into alternative materials. I glossed over this in my tower presentation this morning, but improving the manufacturing processes, looking at different techniques. So you can see the difference in different types of steel from my LCA earlier that looked at each different type of steel was made via a different process. And you can see the core performance differences between those steels. Heat recovery is a big thing with manufacturing steel. There's a lot of heat related problems in frankly, any manufacturing processes. So using technologies like carbon capture storage or hydrogen, biofuels, so on can all make your facilities greener. And of course, general efficiency. So keeping your port distance and your site distances relatively short, improving your O&M practices. So I'm involved with a lot of work with things like condition monitoring and kind of machine learning and stuff like that. These kind of new O&M practices will hopefully help our turbines last longer, which will improve your overall lifetime. And of course, improved installation and assembling. So some of the structures I mentioned earlier, such as barges, are well suited to some of those pros, and the fact that you can build them at port and send them away effectively. So I just wanted to touch on what my initial reference floater will be for the remainder of the project, but this could change potentially over time. But I feel like I've identified concrete as a good opportunity for looking into a new material. So I'll set concrete as my choice of materials. Additionally, I found that the semi-sub is a lighter structure. It's also far better studied as well. So I've got lots of reference models to look at dimensions. So when I'm engaging with manufacturers, it's a lot easier for me to suggest or other people to look at what kind of sizes they want to make, what kind of components we're building in what way. So that's where I'm sitting right now for this project, but that could change over time as well. So just as a quick conclusion, we've looked at the current state of the art for floating wind foundations. We've looked at a comparison between each of these core structures. We've looked at the pros and cons between steel and concrete. We've looked at a basic LCA. We've identified some potential future opportunities, and we've defined our reference turbine, our reference floor, should I say. And last, I've got all my references to any figures I've used there as well for when we circulate the slides afterwards. Thank you. I hope you enjoyed that and got something out of it. Thank you.
Great. Thanks very much, Dylan. Another excellent presentation. Just a couple of questions from me before we go on. I suppose with concrete, have you done an analysis of the sort of amount of rebar that would be required for some of these structures in terms of just comparing sort of concrete with rebar with just ordinary steel use?
Yeah, that's something I would like to look into next, actually. So as I kind of meant, like at the core, it seems like the numbers seem very good, but that was something we didn't really consider. when we were looking at that initial LCA. So that will be something I'd like to consider going forward, just as an improvement point. There's also like the kind of end of life side of things as well. So like steel's very easily recycled, and most of the steel we get in the UK is scrap actually. So there's that aspect as well that I need to build on as well. But I think the early signs for concrete are promising from a kind of emissions reduction standpoint.
Yeah, and the other thing I was thinking of was the sort of strong points that you'd need in concrete for sort of foundations, so for mooring line anchoring, that sort of thing. And I think you mentioned pre-tensioning as well. So, you know, do you do that within a steel section within the concrete? And you know, just how do you ensure those strong points are adequate enough?
So that would be the kind of question I'd like to look into with potential manufacturers as well, because this is something, because some of these structures can be quite complicated geometrically. Yeah. So I've seen some that use the kind of internal steel as a way of kind of modeling it around effectively. But I would be interested in seeing what kind of deviations there are between each of these structures, because the shapes of them are very different. So there could be opportunities there as well for improvements. Yeah,
and we had this morning during one of the sessions, and I was thinking about different types of concrete that are on the market now, or starting to appear on the market. And I know that University of Exeter have got some people looking at different types of concrete, which may also not only have good sort of weathering or marine properties, but also have lower carbon content as well. Just having a look at the chat, I think there may be a question coming in there. Yeah, so a question, Dylan, do you think that concrete rather than steel could lead to more localized manufacture?
Yeah, I'd say so, just based on kind of what the UK manufacturing or UK kind of materials side of things is. So yeah, generally speaking, the days of steelmaking in the UK are unfortunately long gone now. So, but just a simple Google search shows me loads of concrete companies based in at least my local area. So I think there might be opportunities there as well.
Yeah, I think it's probably a bit premature to say that, you know, the steel manufacturer in the UK is gone. I think there's interest in trying to address some of the problems that we're seeing here. We can, you know, maybe realise some of those. Vicky,
of course, as well. Sorry, just to add to it. So I mentioned in my tower presentation that there might be a new appetite for manufacturing these tower structures. So there's a facility going up in the Scottish Highlands, for example. A lot of the core manufacturing processes used for these floors, for a steel floor, for example, would be very similar because they're cylindrical, most of these parts as well. So there might be kind of a synergized co-manufacturing opportunities there as well as these facilities begin to open up if they're successful. So that could also be an option. So maybe we might see more steel structures as well.
Yeah, yeah. Okay, great. Question in from Mark Varley. Thanking you for a great presentation, but also asking, have you seen much interest in vertical axis turbines?
So with regards to, so when I was doing the research for this project, I was mostly looking at horizontal in mind. But from looking at the kind of more conceptual patent side of things, I've seen a lot more work there. So there's perhaps that if the vertical axis turbines start to develop more, if we start to see more industrial use there, then maybe we'll see some of those more experimental designs come through. Something I'm quite interested in seeing as well, I do feel like vertical axis are maybe overlooked sometimes in terms of the old reliable horizontal axis that we have these days as well. So I do think there's at least an academic or some loose industry interest there.
Yeah, there was a study done up in I can't remember which Scottish university it was now, with the that looked at the benefits of vertical axis turbines. I think it was done for Scottish Government probably last year actually. A question in from Anonymous, thinking about UK standards. but actually at the moment don't allow the curing of concrete in seawater, which is allowed in Spain. Are you aware of any studies to look at this?
I've seen one or two studies, not specifically on curing, but looking at the kind of core environmental impact of this kind of technology. But that's something that the sustainability aspect wasn't something I looked into much during the initial literature review, and is something I'm quite keen to look on as I go forward, because the curing aspect isn't something I know much about. But I reckon there probably will be work out there somewhere, because I did do a basic read through of some literature beforehand.
Question just in from Lucas. Will the carbon impact of new port infrastructure to handle concrete floaters be considered in your work ongoing?
I would hope so, yeah. So that'll be something, when we start looking at, say, what site we're going to, we'll be looking at where the nearest ports are to that, and we'll be looking at what's available to those ports. And I think we'll likely engage in the people that run these areas as well, and the companies that are based there as well, to make sure that all that stuff's taken into account. What I've done right now is very high level and very just like focused on what the state of the technology is. But that aspect will be further developed going forward.
Yep. And I see that Neil Farrington's put the details of C12, which is a vertical access design, into the chat. C12 is also an interesting one where the above and below water central column revolved as well. So it's a project we were involved in previously. It's got some merits. I always wonder with the vertical access though about access to the actual blades for just maintenance and repair. Question in from Frank. Is there a realistic alternative to steel rebar, which is something that, and is this something that Exeter is looking into? Not sure we'd know whether Exeter are looking into it, but do you think there's an alternative to steel rebar in concrete?
So right now, I'm not aware at the moment, but that'll be something I'll be looking to extend going forward.
Okay. Question in from Alan. Are you looking at drafts of substructures as concrete ones are heavier than steel, thus have a deeper draft, which has implications for water depth?
Yeah, so that'll be something we'll be considering. So right now we're looking at what the kind of, so we have, at least with the CAP, we're quite blessed in the sense that I work with a team that work a lot with modeling for various floating structures. So I have with me a nice plethora of projects to look into. And for that, I'll be looking at specific dimensions for these aspects with these models to put them against each other. Right now, the concrete numbers for the LC are what I'd like, but if I look at these models and I see these differences in the drafts and aspects like that, then I might change my mind, or we might do a deeper dive with an LCA.
Yeah,
to take that into account.
Just a note from Alex Watley at University of Plymouth. The University of Plymouth are actually looking at alternative materials to rebar. So actually, even from Neil Farrington, sorry. So he's suggested me contact Alex, who we know very well. So we'll certainly do that. Thanks, Neil.
Yeah, sounds interesting. Thank you.
Okay, I just want to finally go to the survey question for this session. And Vicky, if you're able to post that up for people so they can see it. So let us know if you're interested in a collaborative R&D project looking at various sort of experimental solutions for different types of foundation other than steel or concrete. So we just want to get a gauge of the level of interest out there from panelists. And if it's something that you are interested in, then do please let us know, give us your contact details and tell us what your interest is, and we can get in touch.
Yeah.
Vicky's
Admittedly, when I wrote up the poll question, I didn't realise that we could put in more than yes or no.
Oh yeah, it's quite sophisticated.
So for future reference, I'll come up with something a bit more well defined in the future.
Okay, brilliant to see. Quite a significant interest there then. So those that voted yes, please send us your details. Let us know who you are and what's your sort of area of interest within this subject, and we'll get back in touch with you. And we'll work with you then to shape what that deep dive project might look like. Okay, brilliant. Thank you very much, Dylan. Dylan, can you go back and answer some of those questions that arose for you? Yeah, just so people have a personalised answer, you can go into a little bit more detail then if you want to.
No problem.
Smashing. Can I now ask Ellen? Hi, Ellen. If you'd like to share your slides and tell us a bit about moorings and anchoring.
Sure. So hopefully that's coming through now.
Yep, I can see your slides perfectly and hear you perfectly. So Ellen, the floor is yours. Thank you.
Thanks, Simon. Yeah, so good afternoon, everyone. I'm Ellen Jump. I'm a project engineer at ORE Catapult. Primarily, my role is supporting the Fulton Offshore Wind Centre of Excellence and leading the mooring and anchoring work stream, as well as some of our dynamic cable work in that area, but also involved in some of our kind of wider floating wind programmes, including this carbon flow accelerator work on mooring and anchoring carbon reduction opportunities. So for the next 20-25 minutes or so, just going to talk through, I guess, a quick intro to the scope of the mooring and anchoring system in this context, and then what the design requirements for mooring and anchoring systems in Celtic Sea and the Cornwall region are, and then what we then think that baseline mooring spreads look like. And then I'm going to talk a bit about our carbon intensity assessment of those mooring spreads. That work's kind of all still ongoing, so we'll just more be kind of touching on our initial findings and what we're planning to look into in more detail over the coming months, and then talk through some of the potential carbon intensity reduction opportunities for mooring and anchoring systems, and highlight some opportunities where I think it would be good to engage with yourselves in the wider supply chain. So the objective of this particular work package of the Cornwall Flow Accelerator is really just to identify potential opportunities and assess potential opportunities for reducing the carbon footprint of mooring and anchoring. So looking at different mooring solutions, comparing those, different anchoring solutions, comparing those at a full system level, and then looking at innovations for reducing material usage. But I think really going beyond just reducing material usage, but using different materials, processing materials differently, transporting and installation changes that might support reduction in carbon footprint. So the approach that we're taking to this work, it's a desk-based study. Stakeholder engagement is quite key to ensure kind of our information and inputs are accurate as possible. Data collection activities, and we're using a life cycle assessment software, SEMA Pro, as well in the work. But as I mentioned, we're looking at determining suitable, kind of technically feasible mooring spreads for the Celtic Sea region, and beyond that as well, but with a particular focus on the Celtic Sea. Considering the whole life cycle, what's then the kind of baseline carbon footprint of a mooring and anchoring system? But I would say with more of a focus on the component manufacture and transport and installation phases, and then looking at either design modifications or process modifications that can help to reduce that carbon footprint. So the mooring and anchoring system, probably most of you are familiar with this, but just in case there's any who aren't so much so, purpose to provide station keeping functionality, number of different components that can be included in the mooring and anchoring system, but it will always have some form of connection between the mooring lines and the floater. Then an upper mooring system, upper mooring section may be connected to kind of the main line, or there could be a shorter chain section, for example, if the line is a different material. And then some optional components, so load monitoring, buoyancy, additional ballast, either kind of clump weights or additional chains. For many mooring spreads, there'll then be ground line, but not for all. Again, depends on the mooring arrangement. And then some form of anchoring solution. So there's quite a lot of different parts of the system that all need to be considered when looking at the carbon intensity overall. And I just thought it'd be worth adding in this slide just to kind of get a feel for how many of these components we expect. So this is based on some previous Centre of Excellence work, and considering 49 gig of floating offshore wind by 2050, we're expecting kind of in the region of 12,000 lengths of mooring line and 12,000 anchors just for the UK alone. So a huge amount of components, kind of more than 6 kilometres of lines. That might be wrong, actually. I think it might be 6,000 kilometres. Looking at that doesn't look right. 6,000 buoys, 17,000 clump weights. So a huge number of components. And then just in a bit more detail, again, to kind of show the spread of different components that we're considering when trying to assess carbon intensity. So I think Dylan kind of touched upon earlier that the tower at the moment is fairly defined. So it's one component you're looking for carbon reduction opportunities in, or one kind of large part, whereas we've got quite a number of different variables to consider here, from the line material, the anchor type, all the kind of jewellery and connecting points, and then even kind of installation aids, some of which are temporary, some of which are permanent. And the selection of some of these will impact others, and depending on the mooring spread, it's often not a direct swap. So moving from chain to synthetic rope, for example, it wouldn't necessarily be the same length of line that's required. So quite a number of different things to consider. Some design requirements then for the mooring system. So kind of general ones here, design life of around 25 years. For this work, so they'll just discuss the various floater options. We're assuming a 15 megawatt turbine and primarily a semi-submersible is our base case, just to have something to go off. Largely the spreads we're looking at though would work for kind of barge or spar systems as well, and we're not going into detailed design in this particular project. Again, excursions, kind of a key factor in the mooring design requirements, so how much platform offset is required, and based on previous work, we've taken 30% of water depth for kind of UK water depth ranges. And we haven't said it needs to fall within a specific footprint, but the footprint should kind of consider the overall wind farm array layout, and turbine spacing of kind of 5 to 10 rotor diameters, which is expected to be about 1 to 2 kilometres just over for 15 megawatt turbines. Redundancy is an interesting point that always gets brought up in kind of any mooring discussion I've been in. And I know there was a question on redundancy this morning. So I've said here, provide a level of redundancy. We're taking that to be as per the definition in DNV standards. And I'm not sure if the question earlier around redundancy and whether the insurance industry will specify this was specifically saying to have additional lines. So sometimes redundancy, the terms used to have, say, rather than 3 lines, 3 times 2 lines or 3 times 3 lines. But actually, as per the standards, a mooring system can be redundant, even if it's a 3-line system, so long as in the event of a single line failure, that system, the remaining components can withstand kind of a 1-year storm loading condition without kind of risk to that turbine in terms of stability or risk of collision with other structures. So yeah, whole debate on redundancy that we could get into, and I think still remains quite a large question for the industry. And one of the things I'd like to look at in a bit of detail in this work is how does the carbon intensity change if you go to not redundant versus non-redundant, but kind of multiple line versus single line systems. And yeah, different developers at the moment, I think, have different views on what will happen in the future. Moving on, fibre ropes not touch seabeds, various load cases, and a couple of points there around line tensions, both during installation and in operation. And then just, I guess, focusing in on the Celtic Sea. So we've got 3 specific sites that are used as reference in this project. The water depth particularly key, so between 60 and around 120 metres. So quite typical of kind of other UK regions as well. maybe around 100 to 110 being average, and kind of different seabed conditions which will affect anchoring options. Most of those reference sites look like they'd be suitable for drag embedment or suction anchors, but we'll compare lots of different anchoring options, kind of like for like, but also look at how these impact the rest of the system design. And then just for reference, some kind of other details on the metocean conditions. We're not kind of doing that detailed level modelling in Orcaflex or anything in this project using metocean conditions, but good to have an understanding of what they are and use those as a kind of rough guide as to order of magnitude of some of the components in the systems. So our baseline mooring spreads then, the first one that we've used is a kind of 3-line catenary system. So chain right from the floater to a drag embedment anchor. And that chain length can vary quite significantly, but typically kind of 4 to 8 times water depth. And that's really dependent on the floater, the size of chain used, the site conditions, excursion limits in reality for that design. We've kind of said that approximately, and I've just put some numbers in here at the moment, we're still doing these assessments, but I wanted to give some kind of indicative figures. That based on the chain weight, that would require around 1,000 tons of chain per floater. And we've said maybe 3 35-ton drag anchors, which will be made from steel as well. So that's kind of there'll be connecting elements as well too, but they're the kind of main parts of that system. Then looking at a couple of alternative spreads. So again, looking at 3-line systems, but both of these use a combination of chain and synthetic rope. So quite a bit less chain, but additional polyester rope. Smaller drag anchors in this case, as there's expected to be kind of lower loads at the anchor. And one of these uses clump weights, the kind of ballast enhanced version. And then the other one, which is a buoyant semi-top, has buoyancy units, which would be plastic typically. So they would also be kind of included in a carbon assessment. So one of the next things that we want to do is to assess overall the carbon intensity of those components, probably in kind of ranges, because obviously there's ranges here in terms of water depth and anchor sizes as well. So we try and set out maybe a rough min and max range just for the components themselves. So the kind of full carbon intensity assessment, though, a few slides on going into that a bit more detail, requires life cycle definition. So not just fabrication and what's included in the components, but as has already been shown in some of the previous presentations, the full life cycle, so transportation, installation, operation and decommissioning from a component level, and then kind of full system. So we've started to consider for steel chain these steps and what's involved in each one. The design obviously kind of lower impact than some of the other stages, but still worth considering. There'll be kind of computing, processing. For modelling, there might be prototyping and testing, although that's perhaps more likely for some of the novel solutions than some kind of previously proven components. Fabrication is obviously a kind of key part of the carbon intensity of things. So the process there, right from raw material, chain fabrication, but then the heat treatment and inspection and everything else afterwards. But the forming and heat treatment probably being key parts there, as well as the raw material. Transportation, so we'll need to make assumptions as to where this raw material is coming from, where components are being manufactured. It's likely with the sort of chain sizes that we had on the previous slide that that's going to be in Asia. So given that, it's likely that the steel plants will also be in Asia too, but there's kind of mill to production facility transportation needs to be accounted for. And then from the fabricated chain over to the UK, either to an installation contractor or direct to kind of site. And then also the kind of vessels, so vessel time, types of vessels, additional equipment required in subsequent phases. So these are things that it's all kind of work in process to quantify these areas, and we'll do these for each type of component as well, or all the major components. Then just comparing kind of for mooring lines, just as a first example, material by material. So looking at chain, steel wire rope and polyester, taking values from the EcoInvent database for the carbon and CO2 equivalent per kilogram. You can see that polyester actually is coming out as higher than hot rolled steel here, but much kind of lighter material. So overall, the steel chain carbon intensity per meter is much higher. These figures, again, still just indicative, but give a kind of indication of the order of magnitude that we expect to see in terms of carbon intensity of different components. But as I mentioned before as well, it's kind of important to remember that it's not necessarily like for like. So 100 meters of chain wouldn't necessarily be replaced with 100 meters of polyester. There's different kind of lengths of components required. And then looking in a bit more detail at kind of the chain fabrication process. So we've managed to get some figures at the moment just from one manufacturer, and they are quite variable. But this would enable us, rather than use kind of general hot formed steel figures, to get kind of raw material figures and then look at the manufacturing process in a bit more detail. And also to see where in that manufacturing process kind of the key energy usage and carbon intensity comes from. So around 430 kilowatt hours of energy per ton used by the chain carousel. So that's kind of the main part of the chain fabrication forming. But there's also significant energy and gas required in the heat treatment stages too. So that's kind of a look at what's used currently and starting to quantify the carbon intensity of some of those key components. But what then are the reduction opportunities? So we've got quite a number of things that we want to look at in more detail. From comparing those mooring line materials, you can see that there's a kind of driver to reduce chain and to reduce steel in general. So for example, using smaller diameter ground chain, use of load reduction devices, which can shave off the peak loads that's experienced by the mooring system, which could enable use of both shorter lines and smaller lines. Shared moorings is an interesting one to consider. I'm not sure actually whether that will require more or less steel. It'll depend on farm layout and how the moorings are laid out, but would be an interesting study just to even look at kind of line lengths, looking at chain system, and looking at where steel wire rope could be used and how that might impact the carbon intensity of the system. It's not something I've seen spoken about a huge amount in floating wind to date from kind of demonstrator projects, but has been used in oil and gas, and also opens up some opportunities for kind of more local supply chain. Then looking at anchors, I already mentioned we want to do a kind of like for like comparison. So anchors for the same holding capacity, what's the carbon intensity of different anchor types? But really I expect that to be looking at reducing steel usage again, material mass, but also reducing the vessel time or reducing size of vessels. And as well as looking at shared moorings, looking at shared anchors. So this can almost have the number of anchors required, but with that you may need longer lengths of chain or other materials. So it's not as clear cut necessarily as shared anchors are a brilliant solution. It's something that we'll need to do some calculations on. And then I think there's probably a number of potential novel anchoring solutions. So just one that I've used as an example there is being developed by Core Power, who are a wave energy converter developer, and under their UMAC project. But they believe that this could significantly reduce steel and might have good applications for floating wind, although it looks like it may be more relevant to tension leg platforms at the moment. Also options to, I guess, replace chain with synthetics, more use of synthetics, again, kind of some opportunities for local supply chain. And as well as looking at kind of polyester, HMPE, which are used to date, nylon as well, maybe investigating alternative synthetics. And I've seen that there's bio-based synthetics now being used in marine rope moorings. So that would be interesting to look into in this context. But I think it's important to kind of note that we expect there's still to be a requirement for chain, and there's lots of opportunities to kind of green the production of components. So using renewable energy, reducing the energy requirements of processes, greener steel are all kind of key options to look into as well. And then kind of transportation and operations. So dependent on components, can smaller, more efficient vessels be used? Are there installation processes that vary with different components that can mean vessels aren't required for such a long time? Potential for alternative fuels, also kind of localized production. What does that mean in terms of reducing transport emissions? Something I wanted to highlight is obviously system reliability is still very important. So from a CO2 perspective as well, if parts are failing and need replaced, then there's going to be additional components needed, additional vessel time. But obviously we want to be looking at reducing carbon intensity, but we want to ensure kind of safe and reliable operation of wind farms, and that we're not doing anything that would impact OPEX. So looking at all of these things, but also bearing in mind that it still needs to be kind of technically reliable solutions. And then just last couple of slides. So future activity, continue on with the work on raw materials, reviewing impact on number of mooring lines, and investigating those opportunities that I just flagged up a moment ago. And then I think some key points where the supply chain could engage, and again, interested to hear thoughts from all of you as well. But input information would be really key. So kind of what sort of component manufacturing processes do you use at the moment, energy intensity, installation processing times. Also, do you have novel components in development or ideas for novel components? Be really interested to hear those. And also to kind of aid with understanding on what the Cornwall area's local fabrication capabilities are, and kind of what we should be focusing on in this project, both from a carbon intensity point of view, but from a kind of local content point of view as well. I think that was pretty much my last slide. I'm conscious at the time, Simon, so you've appeared back on the screen.
No, that's brilliant. Thanks very much, Ellen. I think on your slide before the summary slide, where you talk about local content and capability, that's a discussion we can have with the whole CFA group, I think, because there's lots of good stuff going on, and we just want to make sure that we touch base with all those members of the CFA family. Just a couple of questions from me. When you were describing sort of different types of synthetic rope, you also had a novel. And I don't know if that meant there was something out there that you thought was bubbling up, or whether you just had that as a sort of catch-all in case something comes up.
There are, I think Kevlar has been spoken about. I'll be honest and say that there's lots of different terms used for the different synthetic rope materials. Yeah. Some of them are trade names, some of them are the raw materials, and I'll possibly tie myself in knots or say the wrong one, but there are definitely novel ones being developed. And I think probably scope for others. I think that kind of concept of biomaterials is really interesting as well. Yeah,
yeah. I don't know if you listened in on the morning session, where that question about insurance and insurance companies driving the need for a redundancy within the mooring system. And I know that certainly the Floating Offshore Wind Centre of Excellence are looking at an alternate or a new type of insurance vehicle for the floating offshore wind market that sort of takes into account issues around moorings and potential for redundancy. And I didn't know if also you were looking at, packing density of floating foundations, and whether there was an opportunity to share moorings or not, or whether that was just too difficult in terms of loadings and sort of maintenance and things?
So I've not been too involved in the insurance project, and I'm not sure whether it's specifically considering shared moorings. Shared moorings is something that we've talked about a bit within the mooring team, but I think the general view is that it's maybe a bit further away than some of the other things that are more important in terms of getting floaters in the water as quickly as possible, as safely as possible, and making sure the system's reliable. I think I want to look at shared moorings in this study at some level, even just kind of some high level calculations to say, right, what sort of line lengths would you need? How does that compare in terms of steel? But I think there's a bigger question on whether that's going to be taken up by the industry or not. I think there'll also be shipping and fishing considerations as well if you've suddenly got a network of mooring lines in the water column. No clear space between floaters. Yeah, absolutely.
Couple of good points coming in from Ollie. BW Ideal are actually looking at developing a novel mooring material, so something we can go back to him on that. And also there is an insurance work group who's looking at some recommendations around redundancy in moorings, very much in favour of redundant systems.
Okay.
Which then does coincide with spacing recommendations as well. Sorry, Ellen.
No, sorry, I was just going to say one of the things that we're proposing working on in the next stage of the Centre of Excellence, although it's, I guess the projects are still to be voted on and decided, is the consequence of failure given different mooring arrangements, and how quickly do you need to get out there, what sort of vessels do you need for recovery. And I think at the moment the LCOE considerations of numbers and mooring lines perhaps haven't gone to that level of detail to consider what happens if something goes wrong. So that's something that we're hoping to.
Yeah, certainly that risk analysis around safety and impact, which, as you say, could drive standardization requirements and things like that, and subsequently cost. Just a couple of questions on the Q&A. And Frank asked about inline tension dampening systems to smooth out peak dynamic loads, and I suppose that I had that similar question. I suppose, have you looked at damping systems generally to reduce mooring loadings and therefore cost? Is that going to be possible?
So I think I had a picture of the Dublin offshore device. So we've determined them as load reduction devices. I think they get called various different things, but it's something that we're considering. We need to essentially review the different options, and we'll need to take it from the word of the technology developers, how much they say they can reduce line size, essentially, because we're not doing kind of detailed system modeling in this work, but would then say, right, okay, if you've reduced your chain size or your synthetic rope diameter by X, then that's a reduction of that in the carbon intensity. We'll need to then quantify, of course, the impact of the device itself in some way, which I think for some of them will be easier.
Okay.
It's something that the Centre of Excellence partners as well, kind of more broadly, are really interested in. So there's a lot of developer interest in those, and something that we see kind of forming quite a big part of our technology qualification programme that we're kicking off shortly.
Okay, be good to see if we can draw some of that into the Cornwall Flow Accelerator work.
Yeah.
Not a question, but a point from Mark about mooring options around plastic buoyancy modules, polyester mooring lines, bio options. He's very interested to sort of more about that. So maybe you can go through these questions that have been sent to you and just type in an answer to give a bit of a fuller explanation. That'd be good. Finally, from Frank, in terms of like-for-like site conditions, is there any sort of magnitude difference between mooring for steel or concrete floaters?
It's not something that I've looked at too much in detail yet. I don't think it would be a huge order of magnitude different, because you'll still want the same sort of stability of your floater for the kind of tower. Obviously the mooring gives that stability, but I don't expect it to be so significant that the results of this don't kind of apply. But it's a good point and something to kind of double check
Okay, brilliant. If I can ask you just to follow up with this, a couple of other questions as well. If you can just look through those, type in some answers, that'd be much appreciated. We finish on this section. Vicky, can I ask you to call up the survey questions on mooring and anchoring? And there was two, I think. The first one was a sort of, that's it, yeah. So if you're currently manufacturing components for anchoring and mooring and are working on reducing the carbon intensity of the components, do you understand the current impacts? Do you need to identify ways to reduce carbon intensity? Are you trying to quantify current impact, or not considering, or haven't considered yet, or not applicable? Just to give us some idea of who's doing what on the call on the delegates list. And Vicky, if you can share with us the answers once they come up. Okay, so unfortunately not applicable for a lot of cases, but it is a specialist piece. Those who said yes or want to consider, make sure we've got your details and we can say shape project or the next phase of work with you. So thanks for that. And Ellen, you were quite, you had a second survey question as well, didn't you? Should we just do that one where we've got the chance? And this was about having technology or process solutions that could make an impact in this area, something perhaps we haven't covered that you'd like to discuss in more detail. So a quite straightforward yes, no, or not applicable. And Vicky, when you're ready for the polling results. Okay, yeah, good. So there are some people out there who've got some processes and things that they feel they'd like to discuss. So please get in touch with us and we'll direct those to Ellen and she can help work with you to shape the next piece of work. Brilliant. Ellen, thank you so much indeed for your time and a great presentation. I'd like to move on now to our industry speaker, and that's Ollie from BW Ideal. Ollie's the Business Development Manager for Northern Europe, and is going to give us some insight into their work and thoughts around concrete hull fabrication. Good afternoon, Ollie.
Thank you very much, Simon. I hope you can all hear me.
Yeah, certainly hear you. I'll just wait to
give me 1 second to set up the presentation. Should be able to see it now.
Here it comes. Yep, we can see that. Over to you, Ollie. Thank you.
Right then. Thank you, and thank you very much to the organizers for inviting BW Ideal. I'll talk a bit about concrete manufacturing of hulls. I'll rectify a couple of misconceptions that have become apparent in previous presentations. Mainly, I want to talk about the local content and local employment opportunities and how we foresee to do the construction of our hulls. Well, before we even start, I need to introduce myself and the company. My name is Ole Stobbe. I'm Business Development Manager for BW Ideal. I've been with the company for over 5 years now. BW Ideal started off as Ideal 11 years ago. It only has one purpose: to design a technology solution for wind turbine support structures in very deep water. So very obviously it needed to be a floating substructure, and we designed this very unique ring-shaped hull. It can be done in squares and circles, but the easiest is if you have a very nice and flat and level surface outside. And besides that technology developer, we have also moved into project development, and we are taking early stage development risk as a co-developer in numerous areas of the world. Quite recently, we were lucky enough to be able to announce that we have won a nearly 1 gigawatt site in Scotland, and we are also active in other parts of the world. We're about, well, we are above 70 people now from all sorts of countries. We have offices with headquarters in La Ciotat in southern France. We have an office in Tokyo, and we have an office in California. So we are represented in the main markets of the world, at least counting per continent. We're listed in the Oslo stock market since March last year. And we're partnering globally with, yeah, all the big names. This should be moving, and it doesn't, which is a bit strange. Okay. We have 2 demonstrators in the water. So after many years of development of the technology, we have come to the point that tank tests weren't enough. And in contrast to many other technologies which have been discussed today, we have operational experience. So the technology is de-risked and ready for commercial deployment. One substructure was realized in Japan. That's the one you see on the right-hand side. It's a 2-bladed downwind machine called Hibiki. It has gone in the water in August 2018 and gone through several Category 5 typhoons since then. So it's proven its worth and it's still operational. So very good example. This one was made from steel with traditional chain link mooring systems. In Japan, there is standards which are, Japan doesn't have standards for floating wind. So we had to use standards that would normally be applicable to shipbuilding. And the reason why we set up an office in Tokyo, amongst others, is to support the local authorities to set up standards that would be more appropriate for floating wind. On the left-hand side, you see the FloatGen project, which is moored south of the Brittany coast near Saint-Nazaire. The turbine is a traditional 3-bladed upwind machine with a capacity of 3 megawatts. It's been operational also since summer 2018, gone through several winter storms, high wave events. The site there is actually a wave test area, so there is a lot of wave there, not such a lot of wind. But I mean, we're there to demonstrate the technology, and the rougher it gets, the better for demonstrating that. So both have proven that it's technically and commercially viable. There is a problem now. My slides can't be moved on. Great stuff. That looks like
about it.
It's crashing. A bit too much for Zoom.
Maybe.
Let me stop sharing and see if I can free up some.
Otherwise, we can run your slides. I think we've got them, Ollie.
Yeah, I changed them slightly. So.
Oh, right. Okay. Let's see if you can rerun them then.
So here we are. Can't see it yet. Don't panic. Back in the game. I hope this works now. Apologies for the inconvenience. I think I did everything that needed explaining in this, but one thing I wanted to make clear is going from the 2 megawatt demonstrator that we have in France, which has a footprint of 33 by 33 meters. We have done design and engineering work towards upscaling the units to accommodate 15 and even beyond turbine sizes, turbine capacities. And we found that for a 15 megawatt turbine, the footprint would be less than 55 by 55 meters. So while the capacity goes up by 650%, the footprint just goes up by some 50%. And this, I think, is in contrast to the comment that Guy made this morning, that 15 megawatt hulls would have a footprint of 100 by 100 meters. That might be true for other technologies. It is not true for our technology. But let's come to the key point of the presentation, and that's the serialized manufacturing process. Here you see an overview of all the processes that would take place in a yard where we do not only the hull construction, but also the integration of the wind turbine. On the back here, you see prefabrication of the rebar. This feeds into a plant where prefabricated elements are made in forms. These prefabricated elements are stockpiled in this area and then taken with a gantry into the production line area. The first stage would be, we'll come to that in the next picture. All of this goes towards a submersible barge. And yeah, let's move on to this video. On the bottom, you see the link to the YouTube site, and I hope a computer doesn't crash this time. Trying to show you that video. Doesn't look very good. All right, here we go. So here's the method of prefabricated elements, which are being assembled and stitched together in the production line. Then you put on the deck elements, prefabricated as well. You do your coating and stitching of the joints, put it onto a submersible barge for launching. The other method we have looked at is gantry slip forming. And you see here where the base slab is poured, and this is pushed underneath the suspended formwork system that sits under a gantry. And while it's being pulled up, concrete and rebar are being fit in. You make the deck from prefabricated element. And we have studied now that we can do it with one gantry rather than two, so that we wouldn't have to push 4 elements onto the deck of the submersible barge for mating. However, in this method, it's done in 4 elements before the entire structure is submerged and towed away with standard harbor tugs to the next position. And then we come to the previous image. Once it's launched, you bring it along the quayside. It doesn't have to be in the same port. And you start with the outfitting. You put on the transition piece, the mooring interface structures, I-tubes, boat landing, put in the manholes, and do all the pre-assembly work. Then you bring it to the next workstation and you install the wind turbine with a land-based crane. We're also studying methods where you can do this with one of these rather older jack-up platforms. And what do we need for this in terms of ports and yards? I call this facilities because we need a level area with a quayside and not really a port. So we would not need to compete with port activities where we would have, let's say, transfer of goods to the quayside or loading, offloading activities. Therefore, we have looked at yards or facilities where we can do the described construction, serialized construction. So what do we need for a production site that can produce 25 units per year? And we've heard that the ambition is that we should do a lot more, like produce 1 unit per week. Then we have to consider a different layout, which would not necessarily be twice the size, but for a 25 unit per year yard, we would need approximately 10 to 12 hectares. The site area would have to have a bearing capacity of 5 tons per square meter. It's very flexible in how you can arrange these production lines. Therefore, I can't give you a certain shape. We would adapt to what we can find in a certain yard. Yeah, we don't need any special infrastructure. So we don't need a dry dock. We don't need ramps or skidding, what do you call this? launching ramps for what you normally use in boat construction.
Slipway.
Slipway, exactly, sorry. We would normally do the launching with a submersible barge. So at the quayside, we wouldn't need a lot of draft with 6.5 meter. We're fairly happy to do the transfer operation of the hulls onto the submersible barge and then go into a different deep water area where we can launch the hulls. For the wind turbine integration, however, we would need a deeper draft, and that depends on the size of the turbine you want to put on. Now with 10 megawatt units, we probably get away with a draft of 10, 11 meters, and with 15, 20 megawatt hulls, we're looking at a draft of 12 meters. So it makes sense to separate the construction side from the wind turbine integration side. Yeah, we discussed the land-based crane, but what we can also do, and which might be easier to mobilize for a small series, is using a retired jack-up crane vessel, which are probably cheap enough to be had in the market because there isn't really much use for them at the time when there's very big vessels in the market for installations. Let me get to the supply chain opportunities. You've seen the processes and it's very obvious what goes into this. It's a very normal, very standard production process that you would see in civil construction for commercial, but also for residential buildings, like elevator cores are being done with slip forming, and skidding is being used in bridge construction. So all of this is standard technology, which is already there. And everything that you know from civil construction would need to feed into this process as well. So it would be aggregate, cement and rebar to make the concrete, and pre-stressing elements in the end. These were mentioned as well, to manage the crack width in the hull and make it resilient against dynamic loading. In terms of equipment, we would need cranes. You've seen a few examples there. We would have skidding systems to create a production line process where the hulls are being moved from one workstation to another. Gantry slipform system is something that wouldn't need to be raised, but then there's all sorts of small elements like cherry pickers and ladders and formwork and temporary scaffolding and this and that. So there is massive opportunities for civil contractors, and to my understanding, there is quite a lot of such businesses, well, anywhere in the UK, but no less in Wales or in Cornwall. In terms of steel fabrication, I mentioned a couple of elements like the transition piece, I-tube, boat landing, and so on. The TP is a rather big beast and contains very thick wall element and therefore needs a specialized yards. But as we have seen previously, there is initiatives to establish such fabrication facilities in the UK. Not in Wales, as far as I know so far, or in Cornwall. So these elements would probably come from a different location, but there is ample opportunities for smaller steel elements that would be like the I-tube, boat landing, etc., which can be done by smaller and local steel yards and boat yards or shipyards. In terms of moorings and marine works, we would rely on chain, fiber rope. We have used a hybrid mooring system in the FloatGen project in France, where we used nylon ropes as a first off. Then, of course, the anchors. There's a variety of anchors that we could choose from. We have a preference for suction anchors, because they can be placed very accurately and reduce the amount of chain that is required to adjust the mooring line length against inaccuracies in placing the anchors. Then Ellen described all the other elements like connectors, inline tensioners, buoyancy elements, and the like. We would need a launching barge, which is normally rented, and we have just recently learned that there is suppliers in the UK that have these barges that would be very close to the specifications that we would need. And then we need the ubiquitous tugs, I mean, just ordinary harbor tugs for moving the hulls around. And anchor handlers, there is, in the UK, there is such vessels, and then of course, marine coordination and execution of works. On the next slide, I would like to present one of the developments, the missing link for floating wind. If you build commercial scale offshore wind farms, then you need a floating substation as well. Unless, I mean, you want to build a very, very, very long length jacket to support the top side. We have done this development in cooperation with ABB, who are now Hitachi, but nevertheless, we have proven the technology, and we can, for different water depth and different marine environments, and we know that this can be delivered, and well, also for Welsh waters, that would be interesting, I think. We mentioned carbon footprint. Oh, there's a mix-up in slides, sorry. Let me go here. We have studied the carbon footprint as well, and I agree with Dylan that concrete has a much better carbon footprint than steel. What I would like to highlight also is that cost is going to play a role, and in combination with the very volatile price of steel and the predictable increase in carbon dioxide taxation or levies, we foresee that concrete will be a lot cheaper in total than steel in the years to come. Right, that's me for now. I left time for questions and answers. I'm happy to take any questions.
Brilliant, thank you very much, Ollie. A great presentation, and glad that the visuals worked out as well. That's quite informative, actually. So thank you very much indeed for that. Some interesting points you raised there, and I was interested in how your sort of 2 megawatt installation, the float gen in France, how you're doing some analysis in terms of how does that scale up. And you sort of corrected the point about platform size that generally increases around sort of 50%. One of the questions I put to Guy this morning, I'll put it to you, is do you see the need for some sort of test platform that either is there to test different sort of mooring designs, is there to test sort of components that are going in the splash zone, or looking at that interface between turbine tower and platform? Do you think there's a need for that? Maybe something that's publicly funded, that's available to developers, or do you feel that things like FloatGen provide a sort of test bed for what you need in the future?
Well, we can use FloatGen for our needs, but of course we can't offer that to other technology developers. So we are looking at the moment at testing methods for change out of major components. We can use our deck for landing the turbine blades, and with an up tower crane or self-climbing crane, that would be an option. So we can play with this, but generally speaking, it depends very much on what you want to test. I mean, a mooring would normally be tested on land in safe environments. If you had to test for impact of marine growth or scour or whatever, you would do that close to the shore, not in a test site far offshore. Yeah, the question is, what exactly do you want to test before you rule out or decide whether to invest in a test site.
Yeah, I suppose the question is for for us as Catapult, when we get approached by supply chain companies with innovative technology, it's quite often a case of, well, you know, where do we go to prove that it does what it says on the tin? And so,
yeah, I mean, the best is to test it in practice and have a discussion with the usual suspects, so those people who are operating this equipment. And there is a couple of units which have been used and are in operation at the moment, and where such things could be tested. And we are always interested to hear about innovations that can reduce the cost or increase reliability, accessibility, availability, things like that. Anything that helps us to improve the business case, of course, is very, very welcome. Now, my view is that there is already so many technologies in the market that if you wanted to create a test field like it has been designed at some stage in the Celtic Sea, this might be probably too late to facilitate the realization of technologies which, yeah, I mean, the market maturity is what dictates what is going to be realized. And then for latecomers, it's going to be very difficult to win this uphill battle to get market maturity and scale up, etc. So that there have been so many test fields or test areas, and they haven't been used very much, that I'm a bit reluctant to recommend anyone to invest in developing any further test fields.
Yeah, it is a very difficult decision, and you know they become very expensive to maintain. I just wanted one more question from me before we go on to questions from delegates. Great part of your presentation around sort of serialized manufacture and slip forming. And when you brought those various parts of the platform together on the barges and then joined them up, I just wondered, I'm assuming there's lots of different sort of cabling and ducting interfaces between those different sections. You know, those just aren't hollow areas. And I suppose it's akin to shipbuilding in a way, isn't it? Where they can manufacture different parts in other places and then bring them here. I just wondered how much pre-installation of cables, ducting was required, or would it all be done afresh on the barge once the sections are joined up?
Yeah, I think it would be significant amounts of work to prepare this, and it needs some smart engineering to prepare well for this, but it's standard practice in all sorts of applications when you connect caisson elements, for instance. This is how you do this as well. So, but I should stress this is an animation that was done, I think, in 2019. It illustrates very well how we want to do things, and it doesn't in a way, because since then we have made progress. We're partnering with Bygging Uddeman from Sweden, who are the technology leaders for these large gantries, under which you can suspend the formwork. And at the time when this was designed, the response was, okay, we can do it up to 40 meters. Now, 40 meters would not be sufficient for a 50 megawatt hull. And therefore we decided, okay, we play it safe. We build something where you can do elements and then stitch them together in the end. But it would be far more practical to do it in one shot. And that's what we want to do. And at the moment, we have confirmation that in general, it's possible to have something that has a span that can do the gantry slip forming in one shot. And we're just in the process of kicking off some detailed engineering work to assess what the weights would be, what the dimensions would be, what the cost is going to be.
Okay, brilliant. A couple of questions from delegates, one from Frank. It sort of says he can understand the ideal barge could be concrete or steel, but is there a preference for concrete for the Celtic Sea due to local content or overall cost, or both? Is that something you can share an insight on at this stage?
Yeah, of course. Well, there is, of course, we would always like to do local content, and our employers and all the developers would do place a lot of emphasis in local content, and that's why I only showed you the concrete construction method. Now,
yep.
A very simple truth is if we build more than 5 units, steel is going to be more expensive than concrete. And therefore, if we go for commercial scale projects or pre-commercial scale projects, nobody will think about steel. It's, yeah, too expensive. Even if you do it in China and then ship it over to the Southwest into the Celtic Sea for final assembly, it's still more expensive than anything.
Okay, that's interesting. That's interesting. A couple of questions from Mark Varley. One is a general thank you for your presentation. You mentioned a preference for suction anchors and just asking to share email addresses. So if you're happy,
you see my email address on the last slide I showed.
Yeah, it's there actually. Yeah, you're right. Good. And finally, a question from Mark. Are you testing different types of scour protection?
No, we don't. For suction anchors, to my knowledge, you don't need scour protection. For drag embedment anchors, you don't need scour protection. I mean, it's a matter of designing the mooring, and the main concern there isn't scour. It's mainly abrasive action of the seabed against whichever material you have on the seafloor.
Yeah. Okay. Brilliant. Okay. Thanks very much, Ollie. I just want to share some final slides and really ask the other presenters to join us just for the opportunity to think of any final questions for everyone. So Ellen and Dylan, don't know, Dylan, if you're there.
Yeah, absolutely.
Yeah. And I suppose it's a question I posed this morning about making sure that, you know, when we're doing our sort of over the horizon scanning from a CFA point of view, we're making sure that we're joining up the work we're doing. So making sure that we're looking at platform designs at the same time as taking into account mooring considerations and vice versa. And then sort of, you know, liaising with industry, people like Ollie and BW Ideal around what they're doing from a practical point of view. And Ellen, Dylan, do you think we're doing enough of that at the moment?
Yeah, I mean, I think as the project progresses, I think it's important that we keep speaking, but I know Dylan and I have had a few conversations around kind of what assumptions we were making in terms of the site, whether the work that we're doing in parallel ties in, making sure we're not making conflicting assumptions, making sure that, I mean, we're both kind of focusing on semi-submersibles, for example. I think now that we have a better understanding of our approach, having gone through those first few months, there's more opportunity to engage with industry and kind of verify some of those assumptions and go into a bit more detail going forward.
Mm-hmm. And to just even from some of the questions and answers we got from our sessions today, actually, so like I was asked a question on, say, curing concrete in the UK. That's something that I hadn't really considered before. So there's these specific aspects that were raised in this same webinar are things that I can take into account going forward as well. So it gives me a really useful barometer for going forward now as well. So these sessions help as well.
Yeah, good. And I think Ollie raised a really good point about substations as well. And that, you know, I suppose some of those nearshore floating wind arrays may have a more conventional fixed bottom substation, but it's more than likely that we need sort of floating designs in the future. So I think we need to put that onto our list of things to do and look at. But I just wanted to check whether Dylan or Ellen, you knew of any work we were doing internally on floating substations.
So we ran a project, a techno-economic comparison of fixed versus floating substations that was published last year sometime. kind of fairly high level, kind of fairly small internal project, but did get some industry input into that. So Ideal supported that with through some interviews and looking at kind of what the crossover water depth would be between fixed and floating. Didn't go into huge detail on kind of substation design, but we do have a kind of floating substation sizing tool that's just Excel based that can be used to kind of say, if you've got this sort of topside mass, this is what size your substructure needs to be. And that was used for that techno-economic piece. So we've got that we can use. We're talking in the Centre of Excellence. So there's a lot of debate now about seabed substations. So we're talking about potentially extending that to looking at seabed substations as well. And that obviously has a huge impact on the whole dynamic cable array and the topology of the wind farm too. But I think that's kind of hopeful planned work, but we've done that initial kind of comparison study.
The seabed substations, I mean, that's pretty ambitious, isn't it? I mean, where's the benefit of those then?
So I think Aker Solutions and Baker Hughes are the two companies that spring to mind that are really kind of pushing those. And I think Aker have said it's 50% cost reduction, I think, from having that seabed substation. Obviously you need the reliability. You don't want to have to go and do maintenance, but you don't need to, I suppose, motion proof the substation. I think once it's on the seabed, people then strip out a lot of additional things that might be put on substations, like accommodation facilities and things like that. That might need to then go somewhere else. So are you truly?
Yeah, exactly.
50%? Yeah, I don't know. But there's definitely a lot of work going on in seabed substations and what that enables in the rest of the array as well, in terms of kind of connectors and things that are required for that too.
Okay, smashing. I've lost my view of questions from delegates. I don't know if there's any new questions that have popped up. Ellen,
in the chat, DNV have kicked off a JIP on floating offshore substations.
Have they? Right.
So, what's Neil Farrington's asked? What do the panel think of the value of carbon will be recognised in lease, CFD supply chain plan and our consenting decisions?
Maybe one for Ollie, if you can pick that up. This is about having carbon reduction targets in lease consents.
And these, I have no idea. I can't possibly comment on that. I would welcome this very much because it would put us in a very favorable position. But I have not heard any noises, neither from Crown Estate nor from BASE or LCCC to make carbon emissions or carbon footprint a metric in any of the assessments.
Okay. A question from Roger for Ollie, asking why you prefer suction anchors over deep set tensile anchors. I mean, you did mention about accuracy of placing, didn't you, and reduction on chain length.
They're proven technology, they're bankable, you don't need to explain them. I mean, we're open to look at alternatives that might be cheaper or easier to deploy, but the main rationale behind using suction anchors is you can just place them with a rather cheap installation vessel, and then using remote control, apply the suction pumps, and you embed them in the water, in the seabed. With the tensile anchor, I'm not sure what sort of equipment you would need to embed them and bring them to the design depth and to the design holding capacity, which might be very significant. So I know that our engineers are looking at all sorts of anchors, and they're very familiar with the different types of anchors. But unfortunately, I'm not able to give you the full account of why we're doing one or the other.
Okay, thanks, Ollie. Just a note from Justin, going back to the question about carbon intensity, and just pointing out that I suppose has got the potential to be a proxy for local content in terms of reducing carbon footprint. So it's of interest certainly to sort of supply chain in Wales and the southwest, if that came through as a as carbon intensity was made some sort of target, either around CFD or leasing rounds. Okay, I'm not seeing any more questions from our delegates. I'll just check the other. Yeah, I think they've all been covered. Yeah, okay, good. So thanks very much, speakers. Let me just get rid of that. Thank you very much indeed, speakers. Just to whet your appetite for future events coming through Cornwall Flow Accelerator. I did mention these this morning. This is the same slide, so nothing new here. But further planned events which would be firming up in due course going into the future. And most importantly, if there's something that you've seen either this afternoon or in this morning's session that you'd like to get involved in, and you'd like to get involved in helping shape a deep dive project, then please get in touch sooner rather than later to let us know, who you are and your interest, and we can start to work with you on that. So just finishing off now, special thanks to all our speakers, those from this morning and those from this afternoon. Thank you in particular to our industry speakers, to Guy Raymond and to Ollie, for giving up their time and providing some real sort of coal-face interest type issues. Thanks to Julie, who organised the event overall. Thanks to Vicky Sharp for managing Zoom in the background. Thanks to Phil Johnson and Neil Farrington from Celtic Sea Power for helping to organise things. That's much appreciated. Thanks then just for participating in this session. There should be a short feedback questionnaire, but I think if you've got the enthusiasm there, you can see the importance of this, this drive to accelerate deployment of floating offshore wind in the Celtic Sea. You should be all over this, so that's good. Okay, so thanks very much. If you're not a member of the Celtic Sea Cluster, do have a look, do join up. It's free to join. Homepage, there's a join button, top right-hand side, and the membership's growing really quickly now. And you'll get through the Celtic Sea Cluster, you'll get posted updates on forthcoming events. That's where we'll host the recordings from this morning and this afternoon's session, and also the slides as well. So thank you very much indeed for your time. Enjoy the rest of the day, and I hope it's sunny where you are. Thank you very much indeed. Cheerio.
Thanks.
Thank you. Bye.
Thank you all. Thank you, Simon.